Hello everyone, welcome to this lesson. So in this lesson, we're going to start a brand new topic, which is called optimization. This is going to be an introductory lesson. In this lesson, we're going to learn what optimization is. We're going to learn what is a maximum, what is a minimum, what is a saddle. We're also gonna learn what is a local versus a global optima. And optima is a word for maximum and minimum. We're going to learn about critical points, which are special types of derivatives. We're going to learn about the second derivative test and why do we need such test. And also we're going to go and learn one of the characteristics of a 2D function, which are contour lines, and also how to graph a 2D function in Excel. And a 2D function is basically a plane that you graph, and we're going to learn how to graph a graph like the one that we have at the bottom left here. Now, what is optimization? Well, optimization is whether you're seeking a minimum or you're seeking a maximum. And that is your optimum value dependent on context. For instance, if I'm dealing with error, my optimum value would be a minimum. I'm trying to minimize the error. But if I'm dealing with, say, a profit, my optimum would be a maximum. I'm trying to seek a maximum of a certain function. If the function is defined in terms of a profit, or again, if the function is defined in terms of an error, I'm trying to seek the minimum. Now, what is the definition of a minimum? What is the definition of a maximum? And what is a saddle? Well, a minimum is defined very, very simply. Well, a minimum is a point in which all the points around that point are greater than it. Like if we look at this point, for instance, and this is a one-dimensional function, a line, we find that here is our minimum, and every point around it is greater than that point, and that is what we defined as a minimum. And the same thing goes for a maximum. A maximum is a point in which all the points around it are smaller than that point. Now, these points have a property that is characteristic of them, is that the derivative is zero at these 2 points. Whether it's a minimum or a maximum, both of them have a derivative that is equal to zero. So if we found where the derivative is equal to zero in a function, we found its optimums. But also we have a dilemma here, because a minimum has a derivative equal to zero, a maximum has a derivative equal to zero. But how do we distinguish between a maximum and a minimum? Well, despite the fact that the first derivative is equal for both, the second derivative is not. And let's look here. If the second derivative is a rate of change of the first derivative, so let's actually see how the first derivative is changing here. Well, here we find each one of those points have a negative slope. So we go negative slope, negative slope, negative slope until we reach a slope of zero. Then it goes positive slope, positive slope, positive slope. So there's a positive rate of change in terms of the first derivative. We go from negative slopes to zero, then to positive. So minimums are known to have a second derivative. So in this case, the second derivative at that negative 3.33 is positive. Now let's look at the maximum. The maximum, we go from positive derivative, positive slope, and we reach a zero, then negative, negative, negative. So you can see there's a negative rate of change for the slope. We go from positives to zero to negatives. And that's why a maximum has a second derivative that is negative. So that is what is called the second derivative test. The second derivative test distinguishes whether I have a minimum or a maximum. So the first derivative finds all the minimums and maximums, and basically those are all the points that the derivative is equal to zero. And the second derivative now goes in and classifies them. The ones that have a positive second derivative, those are minimums. The ones that have negative, those are maximums, and so on. Now, this is for if we're dealing with a 1D function or a line. What if we're dealing with a 2D function like you see here? We're dealing with a plane. Now, the minimums and maximums are still defined the same. The minimum is the point in which it's the smallest point in that region, and a maximum is the point that is the maximum in that region. Now, when we're dealing with a 2D function, which means we're dealing with a plane, there's a third type of point that we come across, which is the point here. If I go in this direction and in this direction, you find that this point is the smallest in terms of these points and these points. So in these two directions, this point acts like a minimum. But what about if I move here and I move here? You can see if I move in these two directions, this point acts like a maximum. And this point is classified as a saddle. It's neither a maximum or a minimum because in some direction it acts like a maximum, in some direction it acts like a minimum. So, and it gets its name from a horse's saddle. Now, another thing I want to go through is that we have two types of minimums and we have two types of maximums. We have a local and a global maxima. And what do I mean by that? A local maxima comes from its name. If I have this point here, this point is maximum to all the surrounding points around it. So this is called a local maximum. And this point is maximum to all the surrounding points. This point is maximum to all the surrounding points. And the same thing goes to this one and to this one. But if I go to this one here, this one, not only is this point maximum to all the surrounding points here, but it's also maximum to everything in the function. So not only is it a local maxima, but it's also a global maximum as well, because not only is it the greatest in terms of every point around it in its local environment, but also in terms of the entire function. So we classify points as either their local maximum or local minimums, or also as global maxima and global minima. Now, another thing I want to go through is the concept of a contour line. And a contour line, if we look at this function here, you see these circles? Now, these circles are actually called contour lines, and contour lines are defined as lines in which every point on them has the same function value. Now, let's actually go a little bit closer in this graph here. This is the y-axis. This is the x-axis. Now, this is the y-axis, and you can see the lines going from right to left here. And those are basically the constant y lines for varying x's. And if I go from outside to inside, these are the constant x lines for varying y's, right? And those contour lines here are basically the points where the function is the same. In other words, this contour line corresponds with 3. So just as long as I remain on this line, for varying x's and y's, the function remains the same. And here, the function remains the same just as long as I'm on this line, and also here and here and here and here. Now, this concept is usually or most commonly used on topography maps, in which it tells you the elevation if you're dealing with a mountain. So those are where those contour lines, those circles are along a map. It tells you the elevation in 2D map. Now, the question here is, how can I graph something like this? Well, to graph something like this in Excel, it actually looks like a grid, okay? Because what I'm trying to do, you see with the ones that I explained, the lines that went from right to left, and those are the constant y lines, and also the constant x lines that went from outside to inside here. We're going to be creating those with a grid. Okay, so what I did here is I chose from negative 1.6 to 1.6. You can choose whichever points you would like. And I went to the increment of 0.2. So now I have all the y's here. And now I went from x from 1.5 to negative 2 at an increment of 0.1. Again, you would use whatever range you would like and whatever increment. And for every combination of both, I got the function value, and the function here for this one is f of xy, x cubed plus 3y minus y cubed minus 3x. Okay, so I came here and got for this y and this x, the function value, and I did this for all of them. Now, let's actually relate this grade to this line. So for constant y values, for this y value, for varying x's, we get, say, this line. And this is, say, for negative 1.6, for varying x's, this is this line. And this is another line. And all of these are different lines for constant y values. And also these are different lines for constant x values, right? So if I use this grid and I graph it on Excel using similar techniques like we did with a normal graph, we get this grid that you can see, those boxes. And what Excel does, it fills in this grid. So it fills in this with a surface. But what we're really creating here is that grid that you see with intersecting lines. Now, to kind of recap, this is an introductory video. So to kind of recap what we learned in this lesson was an introduction to optimization. An optimization is basically we are either seeking a minimum or a maximum, and that will depend entirely on context. If I'm dealing, say, with error, my optimum is a minimum. If I'm dealing with profit, my optimum is a maximum. And we define what a minimum is. Minimum is basically a point that is the smallest in terms of all the surrounding points. And a maximum is a point that is largest in all the surrounding points. Now, we also, in terms of a 2D function, we came across another type of point, which is called a saddle, that whether it's a maximum or a minimum depends on direction. In other words, if we take this point, it's a maximum within these directions, and it's a minimum within these directions, and a maximum within these directions. So it's neither a maximum or a minimum, and that's what is called a saddle. Now, maximas and minimas can also be further classified in terms of either they're local or global. Now, all points, all maximums and minimums are local maxima and minima. And because those points are the largest or the smallest in all their surrounding. But the question here is, are they also global maxima or global minima? In other words, are they also the largest or smallest value in the entire function? And this is also another extra classification that we gave that point. Now, a minimum and a maximum has a characteristic in common in which the first derivative is equal to 0. And this is how we're going to find them, actually. We're going to find where in this function the derivative is equal to 0. In this case, we have negative 3.33 and also at 0. But we have a dilemma here that the first derivative is equal to both of them. So how do we classify them? Well, the second derivative is not equal for both of them. For a minimum, there's a positive rate of change for the second derivative, which is why we have a positive second derivative for a minimum. And there's a negative rate of change for a maximum. That's why we have a negative for the second derivative. So this is going to be our second derivative test. Now, in terms of a second derivative test for a 2D function, it's a little bit more involved, and I want to wait until we actually apply this to a function because it's better understood if it's applied to a function. The last thing that we covered is our contour lines, which are basically lines where the function is constant, or we have the same function value along these circles. And that's most commonly used when in topography maps in terms of elevations. Now, we also learned on how to actually graph this in Excel, and basically we are creating a grid that Excel fills out with a surface after we generate it. And basically you choose all the range of y with the increments that you have and also the x's, and you get the function value for all combinations of x's and y's, and you get this grid that we see here. And these are lines of x values with varying y's, and these are lines of y's with varying x's, and we saw how this looks on a graph and gives us a grid here. Now, the next lesson we're actually going to go into how to solve this function and this function analytically to find the maximas and minimas, like quantitatively, and before we actually go into the numerical methods of solving optimization problems. Well, that's it for this lesson, and I will see you in the next lesson.